Theoretical and practical efficiency of solar cells. We get the solar spectrum. This is our essential resource, and the solar cell converts a part of this photon energy into electrical energy. The power is given by the product of the current and voltage. The maximum power is the product of photocurrent, field factor, and photovoltaic. And the power conversion efficiency is the maximum power over the incoming power of the photons. And we want to see what is the fundamental limitation to the power energy conversion in terms of physical principles. We would use a method derived in 1960 by Shogli and Kaiser, which gives the maximum efficiency based on some assumptions that can later be generalized for more details about a specific technology. So we start with a model that has no limitation for transport, flat bands and Fermi level, good extraction, and the sharp band gap that absorbs nothing below the energy of the gap, and above it absorbs all the photons. And we use this model to evaluate the efficiency of a given solar cell based on this fundamental semiconductor structure. So there will be energy in terms of photons coming to the solar cell. Then the solar cell generates a JV curve. It has a photocurrent, a photovoltaic, a field factor, and the energy is basically a current, electrical current times the voltage. So the voltage is large at large band gap, and the current is large at low band gap. So we will have this basic structure of the possible efficiencies as a function only of the band gap. So there is this method, which is based on the tile balance principle, to obtain, given a band gap, the maximum power that the solar cell can provide. So we consider the fundamental model, as we said. It's surrounded by black body radiation, and it's coming also the solar spectrum. And then the absorbed material is a semiconductor with the sharp band gap, and the only parameter that defines this absorber is the band gap, because it will absorb all the photons when they impact the solar cell. The next assumption is that the recombination losses are minimal, so that we work in the radiative limit, in which all the recombination is radiative emission. Then we can find the photocurrent in the radiative limit, and we can have the photovoltaic in the radiative limit. We have calculated all these things. Based on the voltage, you can calculate the field factor, and then you directly obtain the power conversion efficiency. This is the Shogli-Kaiser method. The main factors that decrease efficiency are the transparent region. You lose a lot of photons that are not absorbed, and the thermalization. Photons with a large energy become thermalized to the band gap, so all the excess energy of the photon is lost, unless you use schemes of multiple exciton generation that can generate more than one photon, more than one electron hole per photon. But this is not the case normally, so that all the photons give the energy of the band gap. And working out these conditions based on these physical principles of the tile balance, we obtain the two main losses is the transparent and the thermalization. And there are additional factors, and the yellow is associated to the field factor, that means the operation point, and the green is the power that can be extracted. So based on the Schoeller-Kaiser method, we can then obtain optimal current, optimal voltage, and optimal efficiency using either the black body radiation to simulate the sun or the AM 1.5 spectrum, which is the solar spectrum. And we obtain these graphs about the ideal photocurrent, the ideal photovoltage, and finally the total efficiency that is possible. This is the result of the maximal photocurrent that one can obtain according to the band gap and the different technologies at the moment of making the stable, how they reach, they approach in the record cells the maximum photocurrent. This is the same for the maximum photovoltage. There is the band gap value. At the operation point, we have less voltage, and the different technologies approach more or less the ideal voltage at the band gap. And this is finally the total conversion efficiency of different technologies. So some of them are above the 75% and others are less, depending on the properties of the semiconductor, contacts, light management, how the solar cell can be made more or less perfect. Now, evolutions of efficiencies, we have the analysis of laboratory cells, which may be rather small, around 1 centimeter square. And this is the evolution of the perovskite solar cell since 2010 to 2020, reaching 25% in different configurations. The general report of efficiency is described in the NREL efficiency table that you can see all the historic evolution of the different kinds of solar cells. In photovoltaic technologies, we have the dominant silicon solar cells and some thin film like CIGS, cadmium telluride, amorphous silicon that are also produced industrially. The dominant is the silicon made from ingots. And here we have the efficiency of solar cell panels, which is smaller than the smaller laboratory cells, which is from 16 to 25% in the case of silicon. Here we can see the maximum efficiency is around 20%. And this is the historical evolution of thin film and crystalline silicon of the prices with respect to the cumulative production. This is the learning curve of the decrease of the price when the production of the photovoltaic technologies is increased.